how did it form? And what impact will it have on its surroundings? To find out, scientists have launched a major international effort to simulate the early evolution of the universe. The action starts a few million years after the Big Bang. Gravity begins to draw hydrogen gas into large halos, and from there into concentrations dense enough for stars to form. As some stars die, they give rise to black holes. These primordial monsters feed on inrushing gas, growing ever larger while blasting their environments with fierce winds and jets. The scene shifts to visible light as the universe reaches its halfway point. Two galaxies are beginning to form, each with a central region densely packed with stars. Gravity begins to draw the two into a cosmic embrace. The black holes at their centers will inevitably meet and merge. The end result, a galaxy similar to our own, with a supermassive black hole hidden deep in its core. We now move to a much larger scale. The action starts 500 million years after the Big Bang. Matter coalesces in a spiderweb pattern of filaments and dense knots. Amid the formation of countless stars, several larger galaxies develop. As they merge, so do the black holes in their cores. By pushing out quasars and the black hole jets powering them are among the most energetic phenomenon known. This one, spotted by the Hubble Space Telescope in the early universe, emits light 600 trillion times brighter than our sun. And yet, that hardly begins to describe the power unleashed when two supermassive black holes collide. To find out what that will look like from Earth, scientists have simulated the moment just before two supermassive black holes merge. Magnetic and gravitational forces heat up the gas. The pair is enveloped in ultraviolet light. Superhot plasma flowing around and into the black holes glows in X-ray light. The intense gravity of the pair distorts and bends space-time, creating a lens. Albert Einstein hinted that the energy of such a collision goes far beyond the emission of high-energy light. His equations predicted that when massive bodies, like black holes, accelerate or whip around each other, they would disturb the normally smooth fabric of space-time. A series of powerful gravitational waves would move outward, like ripples on a pond. By the time these waves travel the breadth of the universe to reach us, their energy will have nearly dissipated. And yet, scientists believe they have detected them. At the Laser Interferometry Gravitational Wave Observatory, known as LIGO, they have assembled precision high-powered lasers and some of the most perfect large-scale vacuum chambers ever created. The idea is that as a gravitational wave passes, it will stretch and squeeze the distance between mirrors placed at the ends of 4-kilometer-long tubes. This distortion of space-time, measured by lasers, is incredibly subtle, 1,000 times smaller than the nucleus of an atom. This ambitious undertaking, decades in the making, finally bore fruit in 2015. The instruments at LIGO and its European counterpart each recorded a signal consistent with the merger of two black holes of 29 and 36 solar masses. Scientists calculate that the collision converted the mass of up to 3 suns to pure energy in the form of gravitational waves. LIGO's founders would win the Nobel Prize for Physics in 2017. This simulation shows the pattern of gravitational waves that the pair would have emitted in the final moments of the merger, and just after. As the objects spiral together, the energy carried by each successive wave rises, for the briefest of moments, to 100 billion trillion times the power of our sun. Collisions like this are extremely rare, but the universe is very large. As their sensitivity improves, LIGO and similar instruments will detect more and more such reverberations in spacetime. Remarkably, even this does not begin to describe the power held within a black hole. Imagine a spaceship in the distant future on a rendezvous with a supermassive black hole. Because of the object's immense size, the stretching force is small, allowing the ship to survive as it falls through the event horizon. But not for long. As the ship spirals down, it hits a wall of energy, what scientists describe as the inner horizon. At a black hole's event horizon, matter accelerates to the speed of light. It is then whipped around so fast that some of it gets flung back out and into a collision with inflowing matter. At the inner horizon, the energy rises so sharply, it may well reach nature's limit, equivalent perhaps to the Big Bang itself. Fortunately, for us, gravity walls off such extremes behind the event horizon of black holes. Wait long enough, trillions upon trillions of years, to a time when theory says all matter and energy will likely fall inside black holes. Gravity may well draw the entire universe inside a single ultimate black hole. Some theories suggest that it could erupt. In a flurry of matter and antimatter. In gases that cool and coalesce into stars. Explosions that give rise to black holes. Galaxies that envelop and nurture them, while giving birth to solar systems like ours. And so here we sit, on a planet that is an infinitesimally small byproduct of the universe at large. Our imaginations, though, are unbounded, as we contemplate the strange and powerful forces that have shaped all we see.